As I've already said, the world is fundamentally dynamic and changing and unknown to the robot. So it does not make sense to overplan and think very hardly about how do you act optimally given these assumptions about what the world looks like. That may make sense if you're designing controllers for an industrial robot at a manufacturing plant where the robot is going to repeat the same motion over and over and over again. You're going to do spot welding and you're going to produce the same motion 10,000 times in a single day. Then you overplan. Then you make sure that you're optimal. But if a robot is out exploring an area where it doesn't know exactly what's going on, you don't want to spend all your computational money on finding the best possible way to move because it's not actually going to be best because the world is not what you thought it was. So the key idea to overcome this, that's quite standard in robotics, is to simply develop a library of useful controllers. So these are controllers that do different things, like going to landmarks, avoiding obstacles. We saw one that tried to make robots drive to the center of gravity of their neighbors. Basically, we can have a library of these useful controllers, behaviors, if you will, and then we switch among these behaviors in response to what the environment throws at us. If all of a sudden an obstacle appears, then we avoid it. Then if we see a power outlet and we're low on battery, then we go and recharge. So we're switching to different controllers in response to what is going on. So what I would like to do is to start designing some behaviors just to see how what we learned in Module 1, a little bit about control design, can be used to build some behaviors. So let's assume we have our differential drive mobile robot. And to make matters a little easier up front, we're going to assume that the velocity, or the speed, is constant, so v naught. We're not going to change how quickly the robot is moving. So what we can change is how we're steering. So you're basically sitting in a car on cruise control where the velocity isn't changing, and you steer it. That's your job. And the question is, how should you actually steer the robot around? So this is the equation then that's governing how the input, omega, hits the state that we're interested in this case, phi, which is the heading of the robot. So phi dot is equal to omega. Okay, so let's say that we have our yellow triangle robot. It's a unicycle or differential drive robot. It's headed in direction phi, so this is the direction it's in. And for some reason, we have figured out that we want to go in this direction, phi desired, of phi sub d. Maybe there is something interesting over here that we're interested in. So we want to drive in this direction. Well, how should we actually do this? Well, phi dot is equal to omega. So our job clearly is that of figuring out what omega should be equal to, which is the control input. All right, so how do we do that? Well, you know what? We have a reference, phi desired. Well, in Module 1, we called reference as R. Right? We have an error, meaning that compares the reference phi desired to what the system is doing, in this case phi, so it's comparing the headings. So we have an error, we have a reference. You know what? We have a dynamics, phi dot is equal to omega. So we have everything we had towards the end of Module 1. So we even know how to design controllers for that. How should we do that? Well, we saw PID, right? That's the only controller we've actually seen. So why don't we try a PID regulator? That seems like a perfectly useful way of building a controller, right? So you know what? Omega is Kp times E, where Kp was the proportional gain. So this responds to what the error is right now. You make Kp large, it responds quicker, but you may induce oscillations. Then you have the integral of the error. So you take the E of tau, the tau, times K sub I, which is the integral gain. And this thing, this integral, has the nice property that it's integrating up all these tiny little tracking errors that we may have. And after a while, this integral becomes large enough that it pushes the system up to no tracking error. So that's a very good feature of the integral, even though, as we saw, we need to be aware of the fact that a big Ki can actually also induce oscillations. And then we could have a d term, so Kd times E dot, right? Where Kd is the gain for the derivative part. This makes the system very responsive, but can become a little bit oversensitive to noise. So, will this work? No, we won't. And I will now tell you why. In this case, we're dealing with angles. And angles are rather peculiar beasts. Let's say that phi desired is 0 radians. And my actual heading right now, phi, is 100 radians. Then the error is minus 100 radians, which means that this is a really, really large error. So omega is going to be ginormous. But that doesn't seem right, because 100 pi radians is the same as 0 radians, right? So the error should actually be 0. So we should not be naive when we're dealing with angles. And in fact, this is something to be aware of, is angles are rather peculiar beasts, and we need to be dealing with them. And there are famous robotic crashes that have been caused by this, where the robot starts spinning like crazy, even though it shouldn't, but it's doing it because it thinks it's 200 pi off instead of 0 radians off. So what do we do about it? Well, the solution is to ensure that the error is always between minus pi and pi. So minus 100 pi, well, that's the same thing as 0. So we need to ensure that whatever we're doing is we're staying within minus pi and pi. And there is a really easy way of doing that. We can use a function, arctangents 2. Any language, there is a library with hashtags, and it operates in the same way. It's a way of producing angles between minus pi and pi. C++ has it, Java has it, MATLAB has it, whatever Python has it. So you can always do this. And how do you do that? Well, you take the angle that's now 1,000,000 pi, right? And you take sinus of it, comma, cosine of it. So this is the same as saying that we're really doing arctan. So I'm going to write this as tan inverse sine E over cosine E. But arctan, or tan inverse, it's not clear what that always returns, but arctan 2, where you have a comma in it, you always get something that's within minus pi and pi. So here's what you need to do. Whenever you're dealing with angles and you're acting on them, it's not a bad idea to wrap one of these arctan 2 lines around it to ensure that you are indeed having values that aren't crazy. So with the little caveat that we're going to use E prime instead of E, the PID regulator will work like a charm. Okay, so here is an example problem. We've already seen this picture. This is the problem of driving a robot, which is the little blue ball, to a goal, which is the sun, apparently. And let's see if we can use this PID control design on omega to design controllers that take us to the sun, or to the goal. And since we're dealing with obstacles, and we're dealing with goal locations, and we're also talking about behaviors, at the minimum, we really need 2 behaviors. Go to goal and avoid obstacles. So what we're going to do over the next couple of lectures is develop these behaviors and then deploy them on a robot and see if they're any good or not.